Alright, good evening and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. I have been out for the last, week and a half, 2 weeks, something like that, dealing with other end of job type stuff. So, we're getting into the point where I have now submitted my letter of resignation because we are leaving. So we're gonna be heading to the UK for 3 years, and we're getting to the point where everybody was like, so when are you actually leaving your job? I'm like, has to be before the beginning of the semester. That's about all I know. So tonight, today is not Mathematic Educator. I am wrong. Goodness. Tonight is Mathematics Teacher, September 2011, which is the October issue. So inside of all of the mathematics teacher magazines, they're similar to Mathematic Educator. We have here a calendar, which is October 2011. I just found this buried in my filing cabinet, and I thought, this actually seems like a good thing to this is a 31 problem challenge, and I want to see if we can just knock them out in 2 hours, just for, some light-hearted entertainment for tonight. Alright, rules are as follows. There are 31 problems. They start in square number 2. We have 4 by 2, 3, 4, 5, 6, 7, 8. We have a 4 by 8 grid. And grid 1 is empty. Or grid space 1. 2, 3, 4, 5, 6, 7, 8. Alright, so grid space number 1. Is empty. And the rest of these are going to be labeled from 1 to 31 as follows. And there is a cordoned off section for each of these things. This is going to make a 3 by 3 and a 4 by 4 magic square when we're done. So all of the answers. Hello there. Enigma. So everybody who's interested, this is Enigma. We're going to be playing with their bot, and there's going to be some. You want to restart Firefox? I don't think so. Yeah. So Enigma worked really hard on getting this bot for a lot of people's channels, and said do you want it on yours? And I was like, yes please, that sounds awesome. Now the problem is that I can't actually hear it. Hello Ames, how you doing? It's probably not your fault. It's I can't hear the raid messages either. Oh, okay. Because I think I had all of my audio go through Stream Elements directly, and so it doesn't link to me. Otherwise, I hear it and then it plays a second time. So could also be something else. I don't know. It's probably not your fault, Enigma. Yeah. Oh no, it's no problem. Definitely don't worry about it. just so like everybody is aware, we're also doing a real analysis class over on e to the 2I pi, or Zach. His channel is being converted into a classroom for the next like 12 weeks or something like that. And we're trying to all learn, or in my case, relearn real analysis. So it's a really cool thing. If any of you are at all interested, uh-oh. Variable volume equals 0. If anyone else is interested, head on over to e to the 2I pi's channel and ask Zach if you want to get into. I mean, yes, but at the same time, not really. Real analysis, when I took it, was a master's level class, and it's like master's level 1. My spouse took it as part of her bachelor's as a senior level bachelor's class. But really what it is it's delving into like why do these things work the way they do. So it doesn't actually require like Calc 3 unless you really want it to. So the way that Zach is doing it is trying to make it more accessible to people who may not think that they could do it. And in fact, they can. Oh, right. No, okay. Uh-oh. Yep. Okay. Not working right now. Don't worry about it. It's all good. Do it the old-fashioned way. So yeah, head on over to Zach's channel and oh, cool. Sorry. It's interesting that like AutoMod isn't on there. Well, whatever. Anyway. Yeah. So if anybody's interested, you can also just check out what's going on. You don't have to participate in the class if you don't feel like it. So I am participating in the Tuesday, Thursday morning class, which is it's actually 2 o'clock p.m. my time, but nonetheless. So 2 p.m. U.S. East or 12 noon Mountain Time is Zach's time. So if you want to check it out, you can, again, just go look. And you can also put them on a secondary tab right now, and you can watch it while you're watching me, too. Okay, so this is our key. We're going to be working on this particular thing. And what's going to happen is, as we go through and answer questions, each one of these boxes is going to be filled with an answer. It's just a regular 4x8 grid. And nice try. Okay. It's a regular 4x8 grid, and the first one's blocked off. It is essentially, it looks like a calendar, basically. And again, all these individual problems are typically going to be fairly easy to work with and things like that. And the idea is that you'd hang this up in your classroom or something, and then every single day you just go through and pick a new one. Or ask your students, hey, what's today's problem? All right. If anyone, Loims, has any questions, feel free to put them in chat and I'll answer as we go through. This is just a bit of frivolity and fun because I like that sort of thing. So, yep. And in addition to the 3x3 and 4x4 magic square arrays, allegedly the L-shaped piece in the corner is going to get us a Tribute to a Master of Recreational Mathematics. I'm pretty sure that I know that that is Martin Gardner. May not actually be. Absolutely. Go ahead and post that one, and I will start working on number 1. Aha. Well, that was an easy one. Here I thought it was going to take more time to actually type it out. Alright, so you've got a squared, really. A squared minus 1 is divisible by 8. So that is 8 divides a squared minus 1. Oh, okay. Where A belongs... Oops. That wasn't what I meant. I meant to do it on this keyboard. Nice. Alrighty. And it gives the Discord. That's pretty awesome. I think I probably will be making my Discord public, like, sort of soon. So I'll let you know when I actually activate it and stuff like that. So thanks so much, Enigma. This is really cool. Alright, have fun in class. Okay, so Loims, what else do you know about when something divides another number? Okay. See, this is another thing that Zach does, is he actually has these people like who ask questions come on live. Yeah. So, right. We're going to say that 8k is going to be equal to a squared minus 1, where k is any integer. I don't have it set up, so that's why I said I might make this happen, like, I might make my Discord public, like, soonish, but... Okay, so we're going to say that 8k is equal to a squared minus 1, where k is any integer, and a has to be an odd integer. What do you know about odd integers? Yep. So 8k is going to be equal to parentheses to n plus 1. This could also be 2n minus 1. Like, I don't really care. Where, in this case, n is also going to be an integer. Right, so at this point, it's just going to be like, let's just knock this out and see if we can get related integers in some way, or the right-hand side is going to have an 8 or something else. So we'll see how it goes. So this is going to be equal to 2n plus 1 all squared is going to be 4n squared plus 4n plus 1 minus 1. Right, so then that's going to be easy enough to get out of there. 8k is going to be equal to, this is going to be, let's factor out a 4. And then we've got n squared plus n. Right, easy enough, divide off. So this is going to be 2k is equal to n squared plus n. So here's an interesting thing, right? We can't necessarily just say right now that this is going to work because we don't have something that's like an integer equals an integer. But what can we say about what's here? Right. So the left-hand side has to be even. Right? It's the definition of an even number. It's twice an integer. All right, what about the right? Okay, so you could factor it. And this is going to be n times n plus 1. Okay, what does that tell you? Could be. With this, right, I'd say, okay, what kind of number is n going to be? Like, we know it's an integer, but and let's put it this way. Compare that then to what n plus 1 is going to be. So like you've got a property for n, but you've also got the next number, n plus 1. Yes, exactly. So these are going to have opposite parity. So one is even, one is odd. So it can kind of go either way. Parity just means there are two choices. It's binary, basically. So parity in this case can either represent evenness and oddness, or it can represent positive and negative. It kind of depends on which context you're going for. Could also say parity represents the matchiness of some number, some value, whatever it is that you're going for. Yep. All right, so where do we go with it? And this is one of those things where, like, you've probably already proven this fact. Yep. So again, we can say like, oh, well, n is going to be... So, okay, here's the thing, right? We don't know which one's which. So you could break this into cases and say like, okay, if n is even, we go this way. If n is odd, we go this way. And that's always one way to go. In fact, I would probably have even started that from here. And said, okay, let n equal to m, where m is an integer, and therefore 2m parentheses squared plus 2m is going to be 4m squared plus, I mean, it's like the same argument that we had up above, but whatever, it's fine. Plus 2m, and here we've got 2 times m squared plus 2m squared plus m, and this is now a definition of an even number. And so since both sides are even, we know that this is going to work, right? that this is at least possible to end up getting. Then, right, this is case 1. Case 2 is we let n equal to m plus 1 for m some integer. We get 2m plus 1 squared plus 2m plus 1. All right, and that gets us 4m squared plus 4m plus 1 plus 2m plus 1. And again, here we get a plus 2 at the end, which then we can factor out 2 times all this stuff plus 1. Right, so then this is also even. And so again, in any case that we go, we end up with an even value on both sides, and so it can work. So therefore, 8 is going to be a divisor of a squared minus 1, provided that a is any odd integer we want to pick. So that's one way to go. The other way is to say, okay, if we have opposite parity or consecutive values, then again we're doing m times, jeez, right, we're doing 2m times 2m plus 1, and then here this is just 2 times 2m squared plus m. Hey, I've seen that before. Right, and if we switch it to minus, then that's going to switch this one to minus. So it doesn't change anything, it's just always going to work. And that's another thing, is that if you want to do consecutive values without specifying which one is the higher or lower, like that's another way to do it. So you could say, okay, well, either I have them in order like this, n is the even value, we're multiplying it together, and then n plus 1 is 2m plus 1. Or you say n is going to be 2m minus 1, it's an odd number, and then n plus 1 is going to be 2m, which is an even number. Play then. So, if you want to get all technical about it, no, because you haven't proven that it was n and n plus 1. You would have proven it for n minus 1 and n. Something like that. Honestly, I'm not too worried about it because, you know, you're proving it for consecutive integers. I don't care like what they look like. You're multiplying consecutive integers, and anytime we multiply consecutive integers, one of them's even, one of them's odd, they always multiply out this particular way. They always end up getting you an even value. Right, so we get an always even product from this multiplication, and then getting the n times n plus 1 is just going to show us, okay, it's an even number. So just like we did the other ones, this one also works now. Okay, fork system. Fork system call creates a new process. New process called by fork is a copy of the current process except for the returned value. Okay. This looks a lot like the magic card fork. Wait, come on now. Fun times. PID_T. Interesting. Make two processes which run the same program after this instruction. Right? Get process ID and then return 0. Okay. So yeah, it's going to create two processes with the same commands. Essentially, it's becoming cloned. Yeah. How do you handle both commands in a shell like is and is? I mean, I don't know. See, this is the problem, Blandley. You're gonna have to seek out people with much more expertise in computer science and programming, because like you're getting to the point where a lot of us are just like way over here in our little world, and the computer science you're getting to is well beyond us. Or at least getting there. This is gonna go well. Wait a minute. I'm smarter than this. 2, 3, 4, 5, 6. There we go. Okay. 6 squares in the diagram are to be folded into a cube. A humanitarian wants to know which side will be opposite the one labeled AN. Got it. Can you help them determine the answer? Create 2 child processes to handle each command separately. I mean, it depends on what you're going for, right? Oops. Yeah, I'm off the screen also. Cool. All right, there we go. Go for it. All right, I agree it's going to be MA. So I started folding this in my head. I know that this one is going to end up being, if we consider TA to be kind of the anchor, then the NI and RI are going to fold up, AN is also going to fold up, like out toward the camera. And MA is then going to fall on that top side. Go like that. And it's going to also be toward the camera that way. And then the HU is going to have to fold the other way to make the top. So the HU is going to be opposite TA, and MA is going to be opposite AN. All right, another way to do it would be like, okay, if we fold this up this way, again, this is also going to be folded in the same way into the third dimension. All right, so our first answer. We're off to a good start here. How does transmission delay work if a packet getting into a link while transferring to the router switch from the server host? Here, how does transmission delay work? Bandwidth over data length. I mean, again, this is not my expertise at all, but bandwidth over yes, Automod, it's okay. That's not what I meant to do. Automod, please. Bandwidth over data length. Time needed to push all packet bits on the transmission link. It depends on the size and channel and bandwidth. Okay, formula for transmission is going to be here. L over R, length over transmission rate. Right, so 1500 bytes or 12,000 bits divided by 1200 or divided by 100 megabits per second. It's going to take that many microseconds, right? Makes sense? Okay. So you're talking, what is the transmission delay? And in this particular case, right, now good news. That one right there is actually in that particular article that you sent. So, transmission delay is going to be our length divided by transmission rate, right? And then the propagation delay is our distance divided by S, transmission speed. Okay, so here's the thing, right? Transmission speed and transmission rate are not the same thing. Transmission speed is the speed at which this thing, this data packet, is crossing the distance. So most of the time, it's like near light speed, right? Because it's actually transmitting through fiber optic cable and whatever else. The transmission rate is going to be the like the bandwidth, the amount of stuff that's being transferred over. Sorry, not the amount. The rate at which things are being transferred over. So our transmission rate is going to be stuff like, 10 megabits per second. Whereas our transmission speed is going to be like, this is the example I gave is 2.4 times 10 to the 8th meters per second. Okay, this gives you a delay, which is going to be in microseconds. This is also going to give you a delay, which is in microseconds. But they're not coming from the same thing. This right here, this is just essentially D equals RT. Or in this case, D over R equals T. It's almost the same. This is not actually distance length. This is going to be the length of the packet. So not distance. This is going to be the, again, size of the packet is going to be like, 10, like 100 megabytes or something like that. And then if we're doing 100 megabytes at 10 megabits per second, that's going to get us a, again, 100 megabytes divided by 10 megabits per second. That's going to end up being, oh God, what is that, 800 megabits. So 800 divided by 10 is going to be 80 microseconds. Provided I didn't completely just mess that up, but, What if the packet is segmented? Well, that seems to be a you problem. So, I mean, if the packet is segmented, then you have to calculate, like, how much time is this going to take you? So, the transmission delay is going to be just how long is this whole thing going to take? And like, where are you splitting it up and by how much? So, like, are you going to send some sort of verification like every 10 megabytes? In which case there would be 10, let's say 2 microsecond delays, which you have programmed into the whole process or something like that. I don't know. Silver! Oh my goodness. I take a little bit of time off and everybody's like... Alright. Car is a rectangle. C-H-A-R, char, if you will, but I suspect it's character or something like that. with midpoint or with a point T in the interior. Not anywhere in particular, just, you know, in the middle somewhere. All right, determine which line segment in the diagram has the square of its measure equal to the expression at squared minus ht squared minus, plus ct squared. Okay. So, I suspect, in this particular case, we're talking AT is here, and CT is here. This does not make a right triangle, so we can say that those two are not related directly in terms of this. HT is this one here. It's just RT, isn't it? Great, now prove it. Okay, so I'm going to split this up here and here. I think that's all we need. So we'll go with B and D as these two. All right, so AT squared is going to be equal to AD squared plus DT squared. HT squared is going to be equal to DH squared plus DT squared. And CT squared is going to be equal to BT squared plus BC squared. Okay, now BT is going to be the exact same length as DH. And BC I think we'll keep BC for now. I don't think there's anything we can do that's nicer than that at this exact moment. Okay. So with just those, okay, with just those, we've got AT squared. We can split up into these two things, right? AD squared plus DT squared minus parentheses. HT squared is DH squared plus minus, also minus. Yeah, DT squared. And then plus CT squared is going to be also DH squared plus BC squared. All right. It's a rectangle, so like the sides aren't going to be equal to each other necessarily. So dt squared here and a minus dt squared here are going to go away. Dh squared here and a minus dh squared are going to go away here. And that leaves ad squared plus bc squared. In the diagram, AD squared is equivalent to this bit here, D, whatever this is. It's at the same place as B, but it's going to the opposite side of the rectangle. So AD squared is the same as this. This is also AD, I told you. And BC is going to be equivalent to this one here. So if we let that be E, then yeah, ET. AD is going to be equivalent to ET squared plus BC squared is going to be equivalent to ER squared, which is then equal to RT squared. Shocking. I never could possibly have seen this in a million years. First guess. I don't know how it's going to work, but you know, for the most part, I think the next one's probably going to be IN. One of them's got to be 3, though. By the pigeonhole principle. Right, we have, if we're doing Martin Gardner, and if his name is Gardner, then we have too many letters to do dyads all the way through. One of these has to be a triplet. I suspect there's a question about angles somewhere in here. So we're going to have to label which angle it is, which has then a triad of letters. Okay, 3. Each letter of the alphabet is assigned an integer, starting with 0 equals A, B equals 1, and so on. The numbers repeat after every 7 letters, such that G equals 6, H equals 0, I equals 1, etc., continuing on to Z. What 2-letter word is represented by the digits 1, 6? Right, so we already know, for instance, A, B, C, D, E, F, G, H, I, J, etc. 1, 2, no, 0. Man. 1. Oh my god, why? Do it this way if you're going to be so difficult. 1, 2, 3, 4, 5, 6. 0, 1, 2. Dot, dot, dot. So what this is saying is that we have our position. Position in the alphabet, mod 7. So, if we want to know, for instance, 1, 6, then we have to go through and figure out like which values are going to get us 1 and which values are going to get us 6 as their remainders mod 7. So in this particular case, all of our remainders mod 7, remainders of 1 mod 7 are going to be those in the position of Alright, I guess. Man. You start counting with 0, it throws me all off. So position, I guess technically then it would be position minus 1. Right, so position minus 1, mod 7. All right, that's going to be in positions. So this is going to be, we'll go like this. This is going to be 1, right? Mod 7, getting you a 1 is going to be 1, 8, 15, 22, and 29, which is then outside the alphabet. And then we add 1 to all these. So we get a 2, 9, 16, and 23, which are the letters B, I, 16 is P, and 23 is X, W. Okay, so then 6 is going to be our numbers that are in the 6th position, and then add 7. So again, here we get 13, 20, and then 27 is outside. Plus 1 is going to get a 7, 14, and 21. This is going to be U, and N, and H. No, that's G. Right, which we already knew from the beginning. Okay, so then we've got to look at what 2-letter words can we make up with this. Well, if we get a U as our second letter, it being the one of 2 vowels, then we say, okay, we can't do B-U, I-U, P-U, probably not. W-U would be a name, but probably not. Okay, so it's not going to be, most likely, not going to be U, which means that the only other vowel is going to be I. And again, we already know what it should be. IG doesn't work, IU doesn't work, IN does work. So, hooray! It worked. Alright, so that's 1, 2, and 3. Alright, 4. Graphs of the equations y equals 3 to the x and y equals 12x minus 9 intersect. Find the sum of the x values for all points of intersection. Okay. So, should be an easy one. Oh, wait. Oh, it's a 3x3 magic square, so it needs to be less than 9. So with this, we've got 3x is equal to 3 to the x is equal to 12x minus 9. Okay, interesting. All right, so if we're looking at these, so we're not going to be able to solve this nicely. Or are we? No, not really. All right, 3 to the x could be equal to, we could take out a 3 over here and get 4x minus 3. It's not like it really matters all that much, but if we divide both sides by 3, this gets us 3 to the first divided out from 3 to the x. So this is going to be 3 to the x minus 1 is equal to 4x minus 3. Just trying to see if it would be at all nice in any way, shape, or form, just to attempt to solve something like pseudo-algebraically, get some ideas over here, throw that out there. So in this particular case, we do see that the graphs of 3 to the x minus 1 okay. Let's get it on the line just for fun. Okay, so we get at x equals 1, our right-hand side, left-hand side is going to be 1. We end up with 3 to the 0, so we get a value of 1. Let's see, so we can get... You know what, let's try it. If we make it nice, right, that's going to go here. Our straight line is going to go through 0, negative 3. And it has a slope of 4. 2, 3, 4. So it also is going to go through 1, 1. It's going to go like that. Right, and it doesn't matter where it goes downward, but might as well just put it in anyway. And then our exponential function is going to triple. So when we move over 1, it's going to get a value of 3. And as we go left, this is going to take 1/3 of that amount. It's going to get us about here. 1/3 of that, it's going to be here. 1/3 of that, it's going to be like here. So then this is going to go... Ugh. It was going so well for a little while there. And then that happened. It's just right there. That's when I decided to change something. No, it's way steeper than that. Okay. So, 3 here is going to have a value of 3 minus 1 is 2, so that's going to be 9. 5, 6, 7, 8, 9. Oh, is it exactly that? That's nice. So 3 is going to be 12 minus 3 is 9. Yep. Cool. So close. Oh my god. I'm having a hard time here. Come on now. Not a function, but you know what? Cool. I used to be good at this. I think I can actually do it on a board better, but anyway. Alright, so 1 and 3 are going to be the two integer solutions for this. Find the sum of the x values of all points of intersection. So 1 and 3, sum to 4. Oh, right, this is not the letter part, this is the number part. Aye. Alright, we'll wait 1 minute while ads are rolling here, and we'll just real quick copy down the problem. You're not missing anything, I promise. You're good. 5. Only 2-digit integers are equal to 3 times the product of their digits. Find the absolute value of these differences of these two integers. All right, back. So there are two 2-digit integers. Are equal to 3 times three times the product of their digits. Find the absolute value of the difference between their digits. If it's a 3 by 3 magic square, I bet I know what the middle square is. Okay, so in this case, what we have is that AB as like a string is going to be equal to A times 10 plus B. So A times 10 plus B needs to be equal to 3 AB. I think if we bring that over to the other side, it's probably not factorable, but worth a shot. 10A minus 3AB plus B equals 0. So 10 times 1 is going to be well, that's unfortunate. So 10 times 1 is going to get us 10. We need two numbers whose three times the product of their digits. Only two 2-digit integers are equal to 3 times the sum of their products. That does not appear to be factorable. Alright, because one of them's got to be... Might have like 2 and 5, but the problem is that they're not being subtracted. These things are being added together. Alright, the 10A and the B need to be added. Which combine their values. So it should make it bigger and make that 7AB, or negative 7AB. Grr. Oh, whoops. That's not what it is, actually. It's not A minus B. Let's find the absolute value of AB1 minus AB2. Alright, we're having some problems with that one, so we'll have to come back, I think. 6. Evaluate 2001. Nope. 2011. Choose 1006. Divided by 2010. Choose 1005. To the nearest integer. Alright, so that's going to be gross, but Using the choose formulas, this is going to be 2011 factorial divided by 2010 factorial. So, not really that bad. So that's going to be 2011 divided by, in the bottom case, this is going to be 1006 factorial and a 1005 factorial in the super bottom here. So that's going to leave a 1006 under 2011. And then we have 2010 minus 1005 is going to be also 1005. And up top in its denominator, that is going to be 2011 minus 1006, which is also going to be 1005 factorial. So those are going away, no problem. So 2011 over 1006, round to the nearest integer, so 2. Number 6. 1, 2, 3, 4, 5, 6. Alright, 7. Guidance is a regular octagon with center 0, or O. 2, 3, 4, 5, 6, 7, 8. Regular. Totally regular octagon. Don't know what you're talking about. Define R1, R2, R3, etc. as counterclockwise rotations of, respectively, 45 degrees, 90 degrees, and 135 degrees about O, which diagonal will be mapped onto CI if each rotation is applied exactly once. Okay, so we want to know what's going to be on top of CI if every possible .45-degree rotation is done once. So that's going to be Alright, so I don't think that this is... it might be. So if it's only talking about R1, R2, and R3, those are the only actual ones here. So a 45-degree angle is going to get us here. A 90-degree rotation is going to get us here. And a 135-degree rotation is going to get us here. So starting with... oh, that's... wait. Counterclockwise. Yeah, cool. And had we labeled this in the other direction, would that have changed anything? Nope. Alright, it's I and C either way we go about it. So that's nice. So the one that's being mapped over there is going to be our diagonal, which we have labeled as GA. Not going to do it now, are you? Smartass. All right. All right, so GA. Really fitting my theory. Yeah. Oof. Had a moment there. Okay. 8. Long way to go. A puppy weighs 3/4 of its weight plus 3/4 pounds. How many pounds does the puppy weigh? Ooh. Okay, weight is equal to 3/4 weight plus 3/4. So we could either subtract this over and make it 1/4 W is equal to 3/4. And so therefore W equals 3. We could also have factored that out and made 3/4 times W plus 1 is equal to W. It doesn't solve for it, but gets the representation a little bit easier to look at in some ways. I don't know, maybe. Okay, in this particular case, right, 3/4 is equal to W over W plus 1. And so in here we see that 3/4 is in fact a number and then a number plus 1. So W would have to be 3 in order to make all that work. Alright, 8. In a group of 50 girls, each girl is either blonde or brunette, and each has either blue or brown eyes. Find the number of brown-eyed blonde girls if 14 are blue-eyed blondes, 31 are brunette, and 18 have brown eyes. Okay, so in this particular case, we create a Punnett square. Make a 2x2 square, which, yes, I know I said I literally just said make a 2x2 square, and I'm making a 3x3 square. Right, if we do it like this, make a 3x3, this also allows for us to have totals. Okay, we'll do capital and lowercase because, you know, that's how they do it in genetics. How does a TCP server client work? What do you get when you cross a rhinoceros and an elephant? Elephino. TCP rearranges data. Rearranges data packets in the order specified. If there's absolute guarantee that data transfer remains intact and arrives in the same order in which it was sent, there is absolute guarantee that data transfer remains intact and arrives in the same order in which it was sent. TCP does flow control and requires 3 packets to set up a socket connection before any user data can be sent. Alright, so it sends a verification that it does have an open channel, and then once it receives verification of the open channel, then it starts trading data back and forth. Erroneous packets are retransmitted from the source to the destination. Process can be broken down. On server side, we have the socket set sock opt bind and then listens. On the client side, the socket is received, sent, etc., and then it connects. Once the connection is accepted by the server, then both can send and receive freely. That's what I got. Yeah, I don't know what to tell you. Alright, so we got 50 total, which is going to go down in the bottom corner. These are hair totals. These are eye totals. And this is overall. Okay, find the number of brown-eyed blonde girls. Brown-eyed blonde girls. That's this number right here. Close enough. 14 girls are blue-eyed blondes. 31 are brunette in total. And 18 have brown eyes. All right, in this particular case, I think you just need you need this stuff for verification. You don't actually need like a huge amount of information. Out of 50, 31 of them are like not taken care of, but are pre-known. So that only leaves 19. Hang on. That only leaves 19 blonde girls because we have 31 brunette. Then that means that of those 19, we know 14 of them are blonde-haired, blue-eyed, and therefore there's only 5 left. And wouldn't you know it, the middle square is a 5. I knew that was happening. All right. Now, just to check, this does leave 13 brunette brown-eyed girls and 18 brunette blue-eyed girls. Going down, this also leaves 32 who have blue eyes at all, and adding across, that also gets us 50, 18, and 32. Cool. Yay, it all works out. All right, 10. Compute the digit in the thousands place when calculating the following sum. 6 plus 66 plus 666 plus 6,666, oops, 6, plus ... all the way up through 6,666,666,666. Just making sure I got the right number of terms here. Compute the digit in the thousands place. So that is going to be this digit right here. What is that going to be when adding all these things up? So how many of these numbers are we adding together in the first place? This is going to be indexed 1, 2, 3, 4. Just tells us how many numbers there are, how many sixes there are put together. So here we get 3, 6, 9, 10. So like we could brute force this, but I'd rather not. And again, what if this was 100 numbers? And so we'd want to calculate what that's all going to get us. Okay, so from the ones place, we're going to get 10 sixes. All right, in the tens place, we're going to get 9 sixes plus the carryover. In the hundreds, we get 8 sixes plus any carryover. And in thousands, we end up with 7 sixes plus whatever carry we get from above. Okay, so this is going to be 60. This is going to be 54 plus 6 is 60. This is going to be 48 plus 6 is going to be 54. And thousands is going to be 42 plus 5. And then the 7 is the term that's going to be left over. Now, in theory, this should make sense with our magic square. Yes, excellent. Right, in a 3 by 3 magic square, all of our rows, columns, diagonals are going to add up to 15. So in this particular case, 3 plus 5 plus 7 is going to get us 15, so good. We verified that our answer of 7 is going to be correct. Now we do know what this number is going to be up top here, right? It's 4 blank 2, so 4 plus 2 is going to be 6, which means that this number here has to be a 9. Can we now reverse engineer the answer? Not really. Okay, cool. Because the distance between the two numbers is going to be 9. All right. 11. All right, give me, all right, let's take a pause here. Go stretch, do whatever you need to, get up, get your water, treat out, whatever you need. Gonna take 3 minutes, and please stick around, support the stream. Thank you very much for coming, everybody, and be right back. All right, back. So, apologies for that, but, you know. Stuck on the proof. Redid all the steps up to where we got to, but now I'm stuck. Okay, so the induction that you were talking about... Wait, no. Oh, did it with induction. I see. Okay. So, this also works in the natural number game. When we were doing some of that stuff. Okay, so for... Sometimes this is also called bootstrapping. What we're doing is we say, okay, step 1. Show that a pattern holds. For the base case. Most of the time this is like n equals 0, n equals 1. You can kind of choose whatever one you want, but most of the time that's just the way it's going to work. 2, we're going to assume that this works generally for totally some unknown n value. So we just call it n. We already showed that it works for the base case. So initially what we're doing is we're saying that, well, it's going to hold for n equals 0 or n equals 1. And that's our assumption. I didn't quite get that in undergrad, but like after I started teaching it a little bit, I was like, oh, that's it? All right, and then step 3 was show, prove that we reach the n plus 1 case from n case. Because if we can show generally that n plus 1 can be reached from n, then that shows that n could be, you know, we started with n equals 0, n could be 1. And then we let n equal 1, and n plus 1 is 2. And then we let n be 2, and n plus 1 is 3. And it just naturally progresses all by itself. Yep. Right, the way that I worked it out, that you can see just above me here, is just a regular math proof. So like this is a standard proof by deductive reasoning. So we are deducing that if, right, if we can express some number, a squared minus 1, where a is an odd number, yes, we're saying if we can express a squared minus 1 as 8k, then we should be able to get down to something that we know is already true. So that's a deductive proof. Yeah, so let a equal, right, we set odd numbers, so a equals 1. Then this is going to say that 8 divides 1 squared minus 1 is 0. So 8 divides 0 is true. Now, if you don't like that one, then go to a equals 3. Right? Who cares? It's all fine. And also, if you don't like this case, you could also say, all right, well, I can't do let's say you can't do a equals 1, a equals 3, a equals 5. Then you could let it be n equals, again, in this case, it would be 0. So then a equals 3 means that n equals 1 for n equals 1 for a equals 2n plus 1. Right, so express your a's as 2n plus 1, and now we can work our way through the natural numbers instead of having to skip count like this through all the odds only. Okay, so if we do let a equal 1 and 8 is going to divide that, then we say that, okay, we're going to let, or assume, assume 8 is going to divide a squared minus 1. And then 3, we need to show that 8 divides parentheses a plus 2 for being the next odd number, squared minus 1. So from here, we need to say that, okay, we assume that 8k is going to be equal to a squared minus 1 is true. Right? And then we know where we need to go. Right? We know where we need to end up. We need to end up here at a plus 2 squared minus 1. We're just not allowed to, like, start there and then work backwards. Or rather, you're not technically supposed to. But you know what? Who cares? Let's do this over on the side. Right? A plus 2 parentheses squared minus 1 is going to be equal to a squared plus 4a plus 4 minus 1. Boo. Minus 1. Which is a squared plus 4a plus 3. Or, no, we can leave it like that. Let's go back. Right, we don't need this stuff. Oops, too far. Let's leave this. Okay, so now what's the extra stuff? It's that, right? 4a plus 4. Did I mess that up somehow? No. Okay. Right, so we have to show that it is divisible by, that is divisible by 8. Right? Okay, so a squared minus 1 will have this work over here. Then plus 4 parentheses a plus 1. And since a is odd, a plus 1 is even. So this means that a could be rendered instead or a plus 1 could be rendered instead as a plus 1 equals 2. I'm not using n, and yeah, I'm using n before. 2m. So this means we got 4 times 2m. A squared minus 1 is equal to, over here we've got 8k. Okay, plus I'm going to leave that off one sec. Hang on. Okay, so nope. Come on now. A plus, please. 2 squared minus 1 is equal to a squared minus 1 plus 8m. So here's the thing, right? If we want to combine these two things, what we can do is we start from the original statement over here. 8k is equal to a squared minus 1. And now we add 8m to both sides. And you're like, wait, what's m? Right? M is any integer. Doesn't matter what it is. It's independent of a or n or anything else. Or k. Right? It is its own integer. Now, some people might look at this and go, what the where did you get this from? But that's not the point. Right? The point here is that we're adding something which is divisible by 8 to both sides. Such that when we have over here, this is going to be 8 times m plus k. Integers are closed under addition. This is still divisible by 8. And this over here is going to be equal to a squared minus 1 plus here we can then again separate this out as 4 times 2m and like you could make this again, let 2m be equal to a plus 1. Now, we could also just jump to like that fact. We could have said, okay, over here, this wasn't m, it was a plus 1. 8 times a plus 1. And again, some people might be like, I don't get where you're coming. It's like this magical thing just appeared out of nowhere. Well, it's not magical. It's that we had to kind of work it out ahead of time where this was going, in order to say, here's what's going to serve the proof the best. So a squared plus 4 times a plus 1 minus 1 is equal to 8 times, again, this would have been a plus 1 plus k. All right, cool. It's an integer. Still equal to a squared plus 4a plus 4 minus 1. And then this is a plus 2 parentheses squared minus 1 equals 8 times an integer. A plus 1 plus k. So this is now telling us that 8 times some integer is going to be equal to this thing when we go to the next odd number, a plus 2 squared minus 1. Sensation. 4 to the negative n equals 32. Find the value of n. That is pre-calculus 1 or maybe algebra 2. So in terms of like age range, most American students are probably learning this in sophomore through senior level of high school. I mean, it depends on where they are. So, like, An accelerated student is probably going to be freshman year of high school. Maybe sophomore. You kind of maybe honors track would probably be sophomore to junior, and then like some crazy like somebody on track for college is probably going to do it junior senior. Yeah, and Loims, you don't need like all of the little tiny bits in there or whatever else, but I would say that this thing, all that stuff in red, is not actually part of your proof, but I would say that it's a necessary bit to work out on the side to say, like, where do I need to go for this? Because I know that I need this thing, right? I know I need this, but you can't, like, just come up with it and then join it back to the original proof. You have to come from the assumption of 8 divides a squared minus 1, and then get to 8 divides a plus 2 squared minus 1. So, like, again, sometimes it's not obvious to see, like, how do you get there, because it's hard. But you need to show, like, how do we get from our original assumption and then progress that to the induction step. Oh my goodness. Sensation, is it 4 a.m. where you are? Alright, tonight is hashtag not sponsored by Pariah Brewing Company. This is the McNeil's Private Reserve barrel-aged stout. 2023 vintage of a rye whiskey. Imperial Stout. Complex blend of 8 different roasted and caramel malts. I can definitely taste it. It's very sweet and also just a little weird. Oak barrel, vanilla, almond, and coconut. It's a little, I think, a little strong for my taste. Not alcohol-wise, just the wow. McNeil's Private Reserve. It's a pretty can, very purple. Yeah, so like the woody flavor of the barrel is very prominent, and I don't know how to feel about that, I don't think. Don't get me wrong, I do have that in several other beers, and Jameson actually has a good like they make Jameson in other barrels, and it was quite interesting to taste that, but again, it was kind of like, I don't know how to feel about this thing. So, Loims, this is also something that happens in Calc 1. So we've talked about this on this stream before. I don't know if you were here or have seen it or whatever, but when you do epsilon delta proofs, so what we're doing is we're trying to say that a limit exists. And if you don't understand the concept of limits, that is perfectly fine. But what we're doing is we're saying, like, if we have a graph, right, let's just do like 1 over n, I don't know, y equals 1 over x plus 3. Right, so 1, 2, 3. Negative. Negative 1 over x plus 3. So we've got this asymptote that goes across like this. And then we have this thing that is coming from negative infinity and then goes like this and gets really, really close to 3, but never actually touches it. This is y equals 3. We want to say, like, what's happening as this thing gets close to either 0 or off to infinity? Like, what exactly is going on? Now, we could do an easier one, which is, let's just pick this number here at x equals 1, right? At x equals 1, we have an actual value for this function, which is that we have y equals 2. And I didn't do this very carefully, but whatever, it's fine. Okay, fine, it's not that fine. Tire stroke. Kill it. All right, there we go. So here, at a half, this is going to be 1. At a quarter, it's going to be a distance of, let's see, this is a distance of 2, so that's going to be a distance of 4, etc. This is going to go down like this. This is going to get closer and closer, essentially vertical, and then it goes off like that because it's really close. So at this value, 1, 2, what limits are talking about is like, how close can we get to this particular value? So if we pick values within a certain distance of 1, then that's going to get us certain values on our function with y values that are within a certain distance of 2. Okay, now in terms of like why these are uneven and things like that, it doesn't matter. It's this particular function that does it. So we're just always saying that this particular distance is what's going to matter. It's one particular distance. I do in a computational sense. I hope that's... I hope I'm understanding you. Okay, anyway, so when we do things like limits, what we're saying is like, in order to get within a certain distance, we'll call it epsilon, of our target value 2, we need to be within a particular distance delta of our target value 1. Yeah, okay. So we've also talked about the notion of distances in this particular stream, or not today, but, you know, in that we say, like, whenever we want to talk about distance, we always talk about the difference between two particular numbers. Yeah, okay. So our x values are going to have a target value of 1. And so we're going to have the distance between them. I don't care what direction it is, but our outer boundaries here are going to be delta away from 1. So the distance, absolute value, between, subtract the numbers, x and 1 must be less than, so it must be within a distance of delta. We just label it delta, right? And if we pick something that is within a small distance delta, like an arbitrarily small distance, like 1/1,000,000th, 1/1,000,000,000th, 1/1,000,000,000,000th of a single distance value, right? Within one atom. Then that looks like a then. I didn't know I was transcribing a doctor's handwriting. Then it must also be true that the values we get back are y values, right? Our y values in this particular case must be within a certain distance of 2. And then that certain distance we call epsilon. It's just going to be the next Greek letter. Now, if we were to actually go through this, I would actually start on this end and say, okay, what's the relationship between delta and epsilon? Because that's going to be much more interesting to me in order to figure out like where we're going to be. So if I wanted to do that, I would say over here, and that's why this is so far out, away from the function, it's away from the red line here, is that we have to encompass all of the red area. And so the furthest out that the red area is going to be is this one right here. I shouldn't have used a curve, whatever, it's fine. So this is going to be the absolute value of negative 1 over x plus 3 minus 2 is less than epsilon. And what I would do is then, again, look at this particular thing and say, okay, what are we going to get for this? Well, if we combine these things, this is going to be absolute value negative 1 over 2 plus 1 must be less than epsilon. This particular thing, I want something that looks like this. So, of course, I had to do the brilliant thing and pick the other one. Oh, I'm such a jerk. All right, F it. We're going to do the easy one because I can't remember this off the top of my head. If we get something like y equals 3x minus 4, right? And x is equal to 1, makes y equal to negative 1. Right? By direct substitution, we can plug that in. If I want to show that the limit as x approaches 1 of 3x minus 4 is equal to negative 1, jerks. Oh, I see. Okay. No, that's cool. Automod is weird. But this is good. Okay, I got it now. Yep. So Franklin, I have done port forwarding, but that doesn't mean I know anything about it. But essentially, you are telling all traffic to go through specific ports as long as it belongs to a specific type. So my Steam port, for example, is like, 29,001 or something like that, or everything between 29,001 and 29,563. And as long as it's Steam and the games that are associated with Steam, it'll be able to move traffic through it faster without having to like double check. I'm not sure about encryption specifically. You just usually designate certain protocols for being within certain port ranges, so that it will be able to send that traffic through. So, for instance, again, I only want Steam to run those particular ports, and if, let's say, somebody else were to come in to my network and attempt to access port 3, right, 00003, and say, I'm a Steam client, I swear, or I'm a Steam server, I swear, my router would be like, no, you're not in the right port, go away. Now, the problem with it, of course, is that, like, Steam always uses 29,000 something, something, something. So, like, somebody could pretend to be Steam and try to plug in for one of these other ports. Limes, so it isn't x minus 1, at least for this. Oh, you're talking about before. Okay, so when we talk about absolute value, we're talking about distance. So again, I know for a fact, 100% fact, that, right, 1, 2, 3, 4. Let's just go nice and easy here. I'm going to have points that go here, right, 0, -4, and then I have a slope of 3. So we go up 3 over 1, get another one here at 1, -1, right, which is the one we know about. And then we go up 3, 1, 2, 3, over 1, get another point at 2, 2. Okay, and then we go like this. Alright, so y equals 3, x minus 4. Right, I know for a fact that it goes through all these points. So what we're going to do is we're going to essentially show, right? We're going to show, goodness. No, because I set port number inside of the router. So it does all of it automatically. We're going to show that as we move closer to an x value of 1 from either side, right? I don't care what side we're on. As our x value approaches positive 1, our y value is also going to approach -1. Yeah, I have used bash like 3 times. And it was all to create some sort of exe file, I think, for Windows. Right, so this is saying as x goes to positive 1, y is going to go to -1. So this is going to say that as the distance between x and 1 decreases, the distance between y and -1 decreases. Okay, so then if we want to talk distance, then we're going to talk absolute value. So this is saying if the distance between x and +1 is going to be some very small number, we call it delta, then the distance between our y value and -1 is going to also be a similarly small number. Infinitesimally small, in fact. Right? As delta gets infinitesimally small, epsilon will also get infinitesimally small. Once we can prove that that is true, then it ends up being that we can show that the limit exists. That, yeah, this limit does show that as x approaches +1, y approaches -1, and therefore the limit as x approaches 1 of this function is -1. It will exist. All right, so what we do in this case, in order to prove definitely that this limit exists, here's what we have to do. We have to start with absolute value x minus 1 is less than delta, and then we have to get to absolute value 3x minus 4 minus -1 is less than epsilon. Right? In order to show that, we have to go in this order. We have to start from a delta, and we have to get to an epsilon. Now, with the knowledge that I have of this particular thing, I can show that the intermediate steps are going to be that we get 3 absolute value x minus 1 less than 3 delta. Okay, now with absolute value here, we could say, okay, 3 is the same as the absolute value of 3. That 3 can come in. We now get absolute value 3x minus 3 is less than 3 delta. Absolute value 3x, okay, minus 3 minus 1 plus 1 is less than 3 delta. And now I can say that the relationship that exists, we can let epsilon be equal to 3 delta. And we can combine these two to get -4. And we can split -1 into a split +1 into a minus -1. And when we do that, we get this last line, which then proves that, yay, it worked. Now, if you're like, okay, cool, but like, how did you do that? What we actually do when we start teaching like calculus classes is we say, okay, look, you're going to see this. It's just going to come up every so often. What you probably want to do is start with the absolute value of y minus -1 is less than epsilon. This is 3x minus 4 plus 1 is less than epsilon. Over here, this is 3x minus 3 less than epsilon. This is the absolute value of 3 times x minus 1 less than epsilon. This is absolute value 3 times the absolute value of x minus 1 is less than epsilon. And This is 3 times absolute value x minus 1 is less than epsilon. And this is the absolute value of x minus 1 is less than epsilon over 3. Now we can let epsilon over 3 be equal to delta, which then gets us absolute value x minus 1 is less than delta. Oh, would you look at that? That's where we start. This is where we need to end. This is our proof in reverse. But what we're doing is we're basically saying, okay, let's just find the relationship that exists. This is the key, really. Let's find the relationship that exists between epsilon and delta and discover it here, doing the proof in the opposite direction. Once we can figure that out, then we can go back and say, okay, if we have this relationship, then we can start from our original position, absolute value x minus 1 is less than delta, and then prove, using all those individual steps, that we end up with the epsilon statement that we needed in the first place in order to solve it. So this is like a long way around to explain that when we're doing this whole induction bit, you may need to do the induction step backward in order to find the relationship, in order to find the thing that you needed to add to both sides, in order to say, here's what I need to add to both sides in order to make this whole thing work in the first place. It's a long way around to say that. I'm very sorry. Small difference in x is a third of the difference in y. Yes. Provided I didn't read it backwards. Yes. And if we look at the actual function itself, right, it makes sense because the slope is 3. So any change that you make in x is going to be tripled in y. Right? The obvious one is if you go over 1, you're going to go up 3. So if you go over 1/1,000,000th, you're going to go up 3 1/1,000,000ths. Would you go that far? Probably not. Goodness. Oh my god. This is psychotic. I love it. Okay, this is S, G, O. 1, 2, 3, 4, 5. 1, 2 ish. Okay, E, U, N, D, R, C. I don't know if that's supposed to spell something, but If we choose an arbitrarily small number, the difference... Right, so the point is still that the relationship is that whatever we pick in one direction, it's going to be 3 times that. Whatever we pick in the x direction, it's going to be 3 times that in the y direction. So that if we pick something that is actually infinitesimal, right, then the difference in the y direction versus the x direction doesn't really matter. So our algebraic solution was, what the hell? I did not click that. Punks. The algebraic solution was this thing. If you're talking about the inductive reasoning, that's this. Isn't what done right? Oh, it isn't. So we showed that we get an even number on both sides, which is going to show us that this is appropriate in terms of having like the appropriate kinds of numbers on both sides. So that up top, like, again, we got an even number. Okay, so let's go through it again. Here we said that 8 needs to divide a squared minus 1 when a is an odd number, odd integer. So 8k minus a, or is equal to a squared minus 1, where k is just some integer. 8k is equal to parentheses 2n plus 1 squared minus 1, because we said it has to be odd, so therefore n can be any integer, and we just make an odd number. This does not say necessarily that there is a particular relationship between the n's and the k's. Doesn't matter. But this is saying that no matter what n and k are, there's some sort of mapping that we can make between the two to make this work. Right? So then we expand everything, knock out all the other things, knock out the common factor of 4 from both sides. So now we have an even number, 2k, where k is some integer, is equal to n squared plus n, which is some other integer. And now we say that, can we get the same kind of integer from both sides? So n squared plus n, we showed, no matter whether n is even or odd, has to be an even number. So there is some sort of mapping that we can make between the two sets that matches an even number with an even number. Works for me. So it's not necessarily like we're finding a specific value. It's just that there is a relationship between an even number and an even number. And we can find that relationship that exists. Yep, that's it. Yep. Has to be divisible by 8. Because otherwise we get that like an even number could potentially become an odd number on the other side. And then we'd be like, okay, well, we can't have that. So we'd have to pare it down even further. But we said that in order for this thing to be divisible by 8, right, the left-hand side had to be just 8 times some integer. And then the right side ended up becoming essentially 8 times some integer. It's just that we knocked it down to become even and even. So are they of the same kind of number? That's all we needed. If we didn't knock out the 4, right? Okay, so let's back that up. If we hadn't taken away that 4 in this step here, then what would we have gotten? Right, we would have had that 8k is equal to 4 times the quantity, n squared plus n, which then makes 4 times n times n plus 1. We proved below that this is going to get us something, which is always going to be an even product. So this is going to be 4 times 2 times m, where m is an integer. Yeah, there we go. So 8m is equal to 8k. So we'd essentially prove in this particular case that k and m have to be the same thing, right? Yep. And again, we proved that that has to be the case. Yeah, it's fine. If you want to work it out, you know, just look a little deeper into it. It's fine.
Raiding party!
All right. So with points C, E, and U being 1/3 of the way through their respective sides of SGO, which triangle in this figure has an area that is exactly 1/7 of the area of triangle SGO? I'm gonna guess it's RDN, but given the fact that I know the answer. Raiders! Good evening and welcome. My name is Obi-Wan Pez. This is NCTM Pachinko. Welcome in from Zax. Hey everybody. Hope you had some awesome real analysis tonight. How'd the class go? Am I a topologist? No. No. So Hypatia, welcome. So I did a bit of research into the right. Yep. I did a bit of research into the Pascal triangle, which then expanded onto a 3-dimensional simplex, which expanded onto a 4-dimensional simplex, and I went, hey, I could generalize this. And so I figured out a whole bunch of properties that were really cool that expanded onto the N simplex, and it ended up being that I called myself N simplex Pachinko because essentially it was kind of like I had actually commissioned, and I suppose I ought to purchase, if he actually made it, a 3-dimensional model of the Pascal tetrahedron, I guess, where if you drop a ball into a cylindrical chute, it will come out and it will fall onto a it will fall onto a central area of 3 other cylindrical chutes and then bounce in one of 3 directions, in theory. So it can either bounce into the A, B, or C chute. Those give you your vectors in terms of which direction we go, and eventually this all builds to like a giant honeycomb network of copper tubing that build up a very nice three-dimensional, in this case, I guess it would be a trinomial distribution. And so it will actually look like a Gaussian. So if you if you excuse my terrible drawing here. Yes, PhD Lingo. It is an awesome little arcade type game where basically I had commissioned him to also purchase like, I don't know, 200 ball bearings, and you drop it into or funnel into one single chute at the top, and then this would all go down like that. And again, it was in 3 dimensions, so it would create this nice little trinomial distribution among the 3 directions that it could go in. So essentially it looks like your Gaussian, but it is in 3 dimensions. Looks like that. So I got one of our engineers he's the lab manager of the engineering department. I commissioned him to make this and then give it to the math department. And this was like, I don't know, a month before we went on break for COVID. So it's been 4 years, and I'm kind of like, hey, did you actually make it? So I got to find out this week whether or not he made it, because I'm leaving. And I'm going to have, if he did make it, then great. He's going to charge our department $200, and they're going to get an awesome little manipulative that they can use. And if he didn't make it, then I'm maybe just going to make my own, I guess, someday. Something. I don't know. We'll see. I'm not very, like, super engineering inclined, but at the same time, in the next day and a half, I need to design a rig that's going to take an airfoil. It's probably made out of, or it is going to be made out of wood. It's going to take essentially two pieces of wood like this. I should have done this on stream tonight, right? Like, would have been great. It's gonna have, let's see, a hole dug out of it here, and here. I can draw, I promise. Nope. Don't do that. And I'm going to fix a pole between them. And in the middle, we're going to have a some sort of airfoil made out of, I'm hoping, craft foam. I've got a problem, though, in that there's going to be a storm coming tonight, or rather at like 4 a.m. And I didn't go to the hobby shop today because I wanted to be on Zach's stream on time. And then I'm going to stick a fan in front of it. Don't blame me. No, I can't blame Zach. But I wanted to be there on time, and I was like, it's now 1:30, and I need to be at home in 10 minutes. So it's gonna send air over the airfoil, and then the point of this is then to show that this is going to create a lifting force. And it's going to be better for some airfoils than others. This rig is going to be, I think, fairly easy to build, and I say that now knocking on wood, because my god, am I going to screw this up somehow. Probably build in struts on either side like this with 2x4 and then a strut across the center like that. It's going to attach these things. So I have like all day tomorrow to do it because we're not going to have school. Yay! So I get to play engineer tomorrow. Yeah. So I'm a math faculty member at a 2-year college in I might as well just do it at this point in Maryland. I'm leaving on Wednesday, so it's not like it matters. And my family is leaving for the United Kingdom in April. So I'm going to be streaming from the UK. I also just figured out that that means that algebraic geometer, nice. One of my colleagues is an algebraic geometer. He's been at it for 30 years. I can't point to like his stuff. I haven't actually looked into it and been like on the archives to look up his name, which is kind of sad. I should have done that. I've been at this institution for 15 years. You think I would have like looked up the people who I work with? So yeah, I'm definitely not an engineer, but we'll see if we can make it happen. My dad, fortunately, is a woodworker, and so like he taught me a lot of stuff. So we're gonna make a bunch of airfoils and stick them in dowels, and so we get like a little dowel like this. We stick it through a craft foam airfoil. It's gonna look like that. We're gonna get one that's just a literal sphere, a literal cube. This is for scouts. Right? So, like, this is going to go terribly for them, but they should probably hypothesize that this is going to be terrible based on their understanding of how, like, the 4 fundamental forces of flight work. Again, those of weight, lift, thrust, and drag. In this case, right, we're just assuming that there is sufficient thrust to get us. Everyone deserves sufficient. We're going to assume that there's sufficient thrust to get us through the air. Night, Danny. Have fun. Yeah, thank you. Yep, I am definitely going to be streaming more. Generally speaking, I do have to get our house fixed up, so like that's going to be a thing. But overall, all right. And since nobody has done it, I'm going to instigate the drop here for yeah. All right. So before y'all leave, I'm going to select a random page here. This is Maine Lingo, a Wicked Good Guide to Yankee Vernacular by John Gould. Oh, this is a good one. There's several on this page. I love it. All right. So this one probably uses the accent a bit less, but gunk hole, Gunkhole, as it sounds. A gunk hole is a small out-of-the-way harbor or inlet larger than an eel rut. Yachtsmen exploring the Maine coast delight in finding cozy and charming gunk holes. All right, it is my intention that at some point in the near future, I am the Gould estate would thank you very highly for that. So I grew up in the Northeast. I'm a New Hampshire boy myself. I lived about here. So pretty close to the New Hampshire coast, in a tiny little town. I think when we left, we had breached 2,500 people, and I think right about now they're around 3,000. Just want to know what do now? Oh no, Zach. All right. Dost thou ihn hoist is something that I came up with as it was the meme of the that 1700s picture. I don't remember exactly what it was, but it was that 1700s picture of the guy in like the frock and the hat going like that. I basically took his picture, and I thought about it, and I was like, I need to make a do you even lift bro meme based on this. So I took his picture like that and put dost thou ihn hoist. So if you've ever seen that on like the meme sites, I doubt it, but that one's mine. So this is a 15-pound weight. I just, generally speaking, do a few curls for like a couple minutes, give or take, because I need to work on my arms. I've always need to work on my arms ever since I was like, old enough to have arm muscles. It was just like, no. My body just does not want arms. So thank you, Zach. Getting me to work on my arms. Actually, in my karate class, right? Like, we do a lot of arm work, and still, my arm muscles are tiny. I just don't understand. It's like my body's just refusing it. I know you have more points, son of a... Switch. I feel like we should have a small number of redeems from one person. Or like, every person can only redeem something every few minutes. Yes. So, I did mention karate, didn't I? I know. So, interestingly enough, my Obi account has 213,000 points. Because I have been monitoring my NSimplex account from my Obi account since I started streaming. And, since I got affiliate, right? That's the only time that I've actually started accumulating points. But Speaking of which, we are coming up on the streamiversary. My official date is sometime in January, I think, but the date at which I have decided, here's where we're having our celebration, is like March something. March 2nd, March 11th, something like that. And we're going to be doing just some basic, yay, we did it kind of stuff. I don't remember exactly what it is, but it's on there somewhere. Oi. Oh. Yeah, I probably should also do something with math in general, but I've kind of wanted the Oi. Okay, that's probably good enough. So I've kind of wanted my redeems to be kind of non-math oriented, just generally speaking. Oh, right, the main lingo thing, right? I grew up in New Hampshire. There is a... God damn it. Zach, you caught me at 3/4 of a pint here. Yeah, so there is a series called Bert and I, which was originally it was a research project done by two guys named Marshall Dodds and Robert Bryan. And the two guys were interested in preserving the storytelling style of the Down East Maine community. And so they decided to... They were two students from Yale back in the 60s, probably, who decided that they wanted to study Down East Maine. And specifically, again, the storytelling style of the Down East Maine people. And so they went up there and they started talking with people and they started listening to stories of people who were around that area and from that area and listened to the accent and started doing all sorts of cool stuff. And they created a series of stories called Bert and I, or Bert and I, which were done entirely in the voice style, the vocal style of Down East Maine. And I remember I went to my local town fair, because we have town fairs up in the Northeast. And that is not... There we go. I mean, if it's going to be my face, right, then I want this to be approximately centered. Close enough. And it's going to be my face. All right. So for a basic one, this one's called Pinon. Let's do Pinon 2. Alright, so we start out standard neutral position, and then we go Jimbi. So we punch out like this, and this gets a little flashy. So what we do is we have a inside out block with our left hand, which blocks out like this, and our right hand goes into an up block as well. So together they kind of come from the Jimbi stance in front of us to the hip, and then snap out like this, And oh, that's embarrassing. There's a hole there. When we block the usually arm that's coming out this way, we then trap it here and smash the elbow here, and then punch the person in the face. So all together, again from Jabi, we go, and then we do the opposite in the opposite direction. So, nope, other way. Something like that. There we go. So then, yup. Right. So it snaps down to this hip, and then we do the opposite in the other direction, like this, and then pop, pop. Right, and then from here, this is going to be a, we come down again to the hip. We do a, I don't have enough room there, whatever. We kind of step out and do a side kick and a back fist at the same time. You can't even see my leg because I can't get it up that high. Pop it back and go into a pseudo. So the pseudo block is something that blocks the sternum to make sure that people aren't going to be able to smack us in the solar plexus, because that's not only painful, but it also stops you from breathing for a second. So we kind of block the solar plexus. Again, get our hand just a little bit out. And then here, the pseudo block is designed to come out and snap against somebody else. And we're usually in a what's called a fugal stance. So we're leaning back a bit on our rear side, and the feet are aligned such that the front foot is pointed forward and the back foot is pointed actually 45 degrees back. Okay, so then we would advance, switch the sides, and then here we'd do a pierce. So this would snap into, essentially right here into that soft tissue. And if you pierce into someone's neck, again, it hurts, and they're not going to be breathing for a bit. So you snap like that. All right, and then from here, it goes into what is called a fugal K. So we come around the complete opposite direction. So we have to come and step way back left like this, come all the way around, block at a 45 back, block this way, and then block at a 45 degree back this way. Okay, then when we're facing, okay, when we're facing this way, then we're coming back to the front, and we step back to the 90 degree mark, and we do, let's see, it's this hand. 1, 2, 1, 2, yeah. So here we come and we scoop kind of downward and do a quick wrap with our fist, and then reverse punch. Nope, not there. Wrap, reverse punch, and there's a front kick in there. Yeah, so front kick is coming up straight in front. All right, let's try that again. So we're facing this way. We're going to back way the hell up here. All right, so we go there. All right, so we come down, scoop, do a wrap, reverse punch, and then a front kick. I can't get it on camera. Front kick, step down, scoop, back fist, reverse punch, and again, front kick, scoop, back fist, reverse punch, and then this one is, I think this one's a twin fist. So you step up again and pop one in the solar plexus, and one in the gut. So this is like, this is a pretty devastating hit when you actually make it. But you come from the front, you bring it back to your hip, snap it forward, and again, this is going directly here, just under the ribs, and then the one underneath. You know what? That's wrong. This is going to this can go to the face. So you're essentially doing a hit to the face and then a hit to the solar plexus. The solar plexus one is really actually what you want to be doing. So it's like you're kind of, as this comes to the face, they're going to be focusing on this. So this is going to get a lot of power into their solar plexus. And that's going to knock the wind out of them and make sure that they, again, can't breathe for a minute. Gives you a minute to get away. All right, and then from here, that's when we do, instead of a Fugelke, where we come all the way back around to do this stuff, instead what we do is we do a down block this way. So it comes down across our body and blocks something that's coming at like our midsection, whatever, and then an up block to the diagonal, and then back and an up block to the diagonal and a yell. I'm not going to yell because, quite frankly, my kids are asleep and I don't need that. They don't need that kind of negativity in their lives. Now you see why it's 5,000. So I have a first degree brown belt in Tang Sudo Karate, which is a sub style of Mudokwan, which is a Korean art. Tang Sudo was the style that Chuck Norris popularized in the United States. And the particular guy who runs our school, or at least used to run our school, was like the guy who actually went to Korea and learned this particular thing. He's a 7th degree black belt or something like that. And it's pretty intense. I have not actually seen him operate. I have only seen, oh no, he's like a 9th degree black belt or something ridiculous like that. But I have only seen the 7th degree black belt in our style. Now granted, if the person at the top just wants another degree, they can say whatever the hell they want. But I think that they have to actually go to Korea to like earn extra grades in their black belt once they get above like 4th. And like talk with the actual masters of this thing. I know that one of my colleagues at school actually went and got his 2nd degree black belt, and he had to go to Japan for his. He's in a particular like kung fu style, I think, which is strange now that I'm saying it, but I think it's a particular Japanese style kung fu, which he went and they actually had a sword. Which, like, they stand there and they raise the sword and, like, you have to get out of the way. So he said he'd been preparing for this for, like, 3 years or something like that. And he managed to dodge the sword, which is not really that surprising. But at the same time, like, I don't know if they were using a bokken, which is like the wooden sword, or if they were using a real sharp samurai sword, which could have potentially really hurt him quite badly. But he said he passed with flying colors, so it was congratulations, sir. So yeah, I have a first degree brown in Mudokwan Tangsudo Karate. Um, and I would be going for black belt in probably a year or two. But I would have to, one, get super serious about doing this and probably go every single day of the week to make sure that I was, like, really getting it. Or I could go maybe 3 times a week and get it in 2. But as it is right now, like, there was not any chance of me getting it in probably the next, like, 3 to 5. I'm just not actually that good. If you're like, what the hell, man? No, I'm actually not quite that good. I like have some interesting ideas about how to move my body and things like that, but I just am not on par with other black belts. Like, for whatever reason, like, something's just not clicking. You know, I put something else in place this year. In like the last 6 months, there was another thing that just clicked into place, and I was like, oh, that's what you meant. I should have understood this like 20 years ago. 5, but I should have understood this 5 years ago when you showed me. But, you know, something just clicked. I was like, that's what that is. So now I am moving to England. There is no Tangsudo Karate as far as I know, at least not in our area. I will be probably expanding out to a different style entirely. My sensei at the one class said, if you go with Kempo, that's probably going to be the thing that's the most similar. Or you could go, like, completely off the wall on your own path and, like, you know, do something different so that you can come back and be like, I understand this other thing. So there's the possibility of me actually getting a black belt in the next 3 years in a completely different style. Oops, sorry. I was not supposed to do that. Just me wielding a knife. It's fine. Yeah, I just realized my mouse pad is, like, so gross. There's actually dirt on here from like 15 years ago that I just never... I mean, I probably should just get a new mouse pad, but, like, that takes work. And, like, going to a conference or something. Or ordering one online. So much dust. That's so gross. Okay. Yeah, so one of my friends was actually in Kempo, and he was a green belt when he came to the summer camp that we were both working at, and he was like, hey, you seem like you want to learn martial arts. And I was like, yes, in fact I do. And he was like, do you want to do it with me? And I was like, sure, why the hell not? So we went up to the waterfront area that was like next to the staff site, and we would do like forms and one step, which is like, I stand there, I go into a Jumbi stance, and then I do a down block and yell. And then you yell, and I try to punch you in the face. I had never done any martial arts at this point. And at that moment, what you're what you're trying to do is block the attack, either through a parry or a block or whatever, and then strike the other person back and or knock them over and or bring them down using some other technique. So one of, there are several really awesome techniques that I have been working out in the last few years. But yeah, he, as a green belt in Kempo, had like several really good ones that I was really squeamish about, because it involves one of them involves a sweep to the leg that could potentially be dangerous if you don't know what the hell you're doing. And like, I did not know what the hell I was doing for a very long time. I've like essentially just begun playing with it because I found another lead-in that works pretty nicely. My favorite one of the new ones that I picked up was, I've been working with another guy who's going for black belt this spring. And when you punch, the movement on this is that you essentially go up and parry so that their arm is coming along the side of your arm like this, and then you come up and over like this, and when you come down with your elbow, it's essentially on their elbow, and it drops their face right here. Right here. And so it was just like, okay, I go up like this, and I drop it down, and I've got your head. And it's like, oh, huh, that's nice. So, Blaine, it all depends on really what you want to do. So if you are going for some sort of... If you are eventually going to want to work in some sort of like applet environment, where you're going to be doing web applets and things like that, Java might be something useful to learn. I'm not sure that it's going to be used, but I would think it would be useful. There's a difference between the two, and I hope that, you know, everybody understands that there is a difference between the two. Useful and used, I guess. Alright, Zach, have a good night. So, this is me just making up. This right here is just me making up for the fact that I haven't been online in like 2 weeks. I will most likely still be on, like, once I actually figure crap out, I will probably be on almost every day. But we'll see how it goes. Like, at some point or another, almost every day. I need to get contractors in to fix all sorts of stuff in our house. But, ooh, goodness. Okay. So if we're doing this as 1/3 times SG, well, we'll do it in numeric or alphabetic order. GS. And this is going to be 2/3 GS. So I think mostly my spouse uses Python, but over the years she has used Perl, Python, maybe a little JavaScript, but maybe also a little bit of Java. I'd say Perl and Python were the two biggest, and then like a little bit of C++ and a couple other small ones that I don't even know. 1/3 GO and 2/3 GO. This is 1/3 OS and 2/3 OS. Okay. I think this one is actually going to be useful to figure out the semi-perimeter. I know. Horrifying. No, wait. There's an area formula that uses the semi-perimeter, I think. She does not do machine learning specifically. Well, okay. I don't know if she uses machine learning, but finding the area of a triangle using Heron's formula. Yes, please. Okay, the area of GSO, whatever it is going to be equal to the square root of the semi-perimeter times semi-perimeter minus OS times the semi-perimeter minus each of them. Yep. GS times the semi-perimeter minus GO. Semi-perimeter is half of all of those things added together. Okay. I think I'm gonna, before the ads hit, I'm gonna preempt this and say, let's take a 3-minute break. Everybody stretch. Cycle your water. Wink, wink, nudge, nudge. And let's all take a quick break. I'll see you all back here in just a couple minutes. Whoa. Obviously, I need to have more water. So, see you back in 3. Thank you for supporting the stream. Thank you for coming in from Zach's raid. And I'll see you in just a couple. All right. Well, now that I'm looking at Heron's formula, I don't know that it's actually going to help us any. Because we also want to look at the other stuff for each of the individual triangles. Again, I'm targeting RDN as like my, I want this to be the triangle that I'm looking at. As the triangle that I think is 1/7 the total area. Now it's possible that it is instead DEG or UNO, ONU, NOU. Right, but I'm targeting RDN because I think it's that one. Okay, so let's see if we can come up with any sort of relationships that are at all helpful. So area from law of sines, maybe? H is going to be the sine of okay. One half AB sine C. That's not right. Lowercase. So in this particular case, GSO is going to be I don't have any angles. Okay, so that's not even going to help. Not sure I see it. Well, again, I should know. I can reverse engineer what the answer is, but that's not fair. So let's skip 11 and go to 12. Three similar rectangles with integral widths and lengths in the ratio of 1 to 2 form a non-convex hexagon. Not exactly that, but close. Yeah, no. Right, so that's going to be 4 plus this other bit. Not quite, but whatever, it's close enough. Alright, totally it's a 2-to-1 ratio. Width of the largest rectangle is 3. Find the sum of the digits of the hexagon's perimeter. So if that's 3, this is going to be 6. If that height is 3, then this is going to be 1, and this is going to be 2. Which means that this is going to be 4, which means that this is going to be also 2. This is going to be also 1. This is also going to be 2, and this is going to be 2. And then this is going to be 6. So find the hexagon's perimeter. Alright, so 10, 18, 20, 22, 23, and 3 is going to make 26. Oh. Wait. Sum of the digits of the hexagon's perimeter, which means it's only... can't be 26 because it's got to be 1 to 16. Only the numbers that are actually used. So 1, 2, 3, 4, and 6 is going to be 16. One, 2, 3, 4, and 6 are all being added, but no other numbers and no doubles. Okay, so 12, position 12. That one? That doesn't make any sense. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. Nope, that doesn't make sense either. 12 should be a single digit number. And in fact, it should be... if it's going to be 15, that should be 8. Should be an 8. Why? Eight. 1, 2, 2, 10. Oh, are we doing the Kabbalah thing where we just add up all the digits? BZ Jedi, good evening and welcome. I have found it very rewarding. What is your background, I suppose, is another question. I've been teaching math for about 15 years, and it has given me the courage to experiment with some things that I wanted to do for class, for example. And I've got several people here who stop in every so often and, give critique and help me out with pedagogical stuff. as well as deciding, you know, what looks good for trying things out. 18, 19, 20, 21, 22, 23, 24, 25, 26. Ah, okay. So yes, it was 26. It was 26, but that makes 8. Because here it is 6 plus 2. So we just add up all the digits and just keep adding. It is the Kabbalistic type numerology, adding up all the numbers until they make a single number at the end. The equation, x squared plus px plus q is equal to 0. This looks an awful lot like a differential equation, I know. Where q is not 0 has two unequal roots, such that the squares of the roots are the same as the two roots. Okay. So here, if we say that this is going to be x is equal to negative p plus or minus square root of p squared minus 4 times a times q all over 2a is 1. Okay, that's what we've got. The squares of the roots are the same as the two roots. No, that's a q. Over 2 parentheses all squared. That is going to be very interesting. So, if we multiply everything out, this is going to be negative p plus or minus square root of p squared minus 4q times 2 is equal to parentheses negative p plus or minus square root of p squared minus 4q parentheses squared. Interesting. So in this case, we also could potentially have, if we just let this be a, this could be a squared, 0 equals a squared minus 2a. A is either equal to 0 or 2. Nope, root 2. So, hang on. Yep, complete all. Okay. Okay, so either all of that stuff is equal to 0 or 2, well, 0 or root 2. Oh, no. 0 or 2. That's fine. Right, because we factor it. It's a times a minus 2. Okay, so that's going to be negative p plus or minus square root of p squared minus 4q is equal to 0, or negative p plus or minus square root p squared minus 4q is equal to 2. Calculate the product of p times q. Oh, good. Oh my goodness. In this case, we've got plus or minus square root p squared minus 4q is equal to p. Square both sides, we just get p squared minus 4q is equal to p squared. Oh, gross. Q is equal to 0? The frickin'... Okay. No, that can't be right. Plus or minus square root p squared minus 4q is equal to 2 plus p. Square both sides. Okay, 4 plus 4p plus p squared is equal to p squared minus 4q. P squareds are gone. 4's can all go away, so negative q is equal to 4 plus 4p. Nope. 1 plus p. P plus q is negative 1. So q is equal to parentheses, or negative parentheses 1 plus p. This cannot be right no matter what. Hum. Plus or minus square root p squared minus 4q. Oh my goodness. Calculate the product p times q. Where do I go from here? Gross. Alright, I'm going to need more time on that one. That's 13. Of course it is. 14. Rectangular sheet of paper. 2 by X. Where X is greater than 2, is cut into 3 congruent pieces by 2 straight cuts, as shown. So somewhere over here. Boo. Give or take. Not shown to scale, etc., etc. Find the number of square inches in the original rectangle. So square inches in the original rectangle. These are all going to be 1/3 of the area, which is going to be 2x. 2x over 3 is going to be equal to the area of oh, right. So this is going to be 2. And then this is going to be 2. Ugh. No, x minus 2. Right? X is the full side. We're subtracting 2. X minus 2. Interesting. Okay, 2 times x minus 2. Let's give it the same as 2x over 3, so we can divide both sides by 2. And we get x over 3 is equal to x minus 2. And multiply by 3 on both sides. This gets us 3x minus 6 is equal to x. So 2x is equal to 6, so x is equal to 3. So it's a 2 by 3. Find the number of square inches in the original rectangle. So area is equal to 6. Major finger. How's it going? 14. Nope. Nope. You jerk. Hi, that's my name. Friggin' A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The hell number was I on? Oh, I love BBQ chicken. 14. 14. 2, 3. God damn it. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, last one there is going to be 6. Does that make sense? 13 plus 2 is 15. Yes. Okay, which means that we know that this is a 1 and that this is a 9, but we haven't actually proven that yet. We haven't actually figured out how in the hell to get those answers. Right. All right. 15. I didn't even ask for that. What the hell? All right, 15. Trapezoids, CPHL. 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 With diagonals CH, PL, and other segments UO. Median OU. CL is 20. PH is 12. UO. D, R, and E. Of the many segments in this figure, which one must have a length of 4? Okay. That's fun. So I think UPHO and CPHL have to be similar to each other. So I think that means that UP, UC, HO, and OL, not between them, but at least among them, have to be the same size. So again, UO is the median. So, Major, is there a particular name you would prefer to be known by? Always fun. So, like the triangle similarity. Can we do something with that? Those are the only two measurements we know. Right, so these are going to be whatever angles they are, it doesn't matter. But if it's a trapezoid, that means that the top and the bottom certainly have to be parallel to each other. in this particular case. And UO, is that guaranteed to be parallel to the two sides? Oops. Yes. Okay, so the tops and the bottoms have to be the same. Excuse me. Which does mean that 12 to x, well, okay, UO, OU, something, needs to be the same as OU to 20. So OU is going to be equal to 240 OU squared. Oh, but it's not the same, is it? It's not similar because it's not a triangle. Nah, can't work like that. Okay. Come on. Okay, so how does it actually work? Trapezoid with median. EF is parallel to AB and CD. Okay, so we have that in this particular case. They are going to be parallel. EF is, interesting. Oh, okay, so OU is the literal mean . 12 plus 20 over 2, which is 16, right? Halfway between each. Okay. What else? These are not necessarily isosceles trapezoids. Okay. So we've got a few different ways we can go about this, possibly. Okay, we've got similar triangles here. We've got like angles here which are the same. Oops, that's like 12 to ER. We don't have any numbers otherwise on any of the other three sides of the triangles. also the same as the giant one. CDL. HDR. What the hell? P. HDP. CDL are the same or similar. So let's see. Angles aren't the same. I'm not seeing it. I think we may have to come at this later. I mean, I know what the answer is, but that's not. That's not the point. Alright, 16. At this point, if we do 16, I'm going to call it half a month, and it will be good enough. And we'll continue it next stream, next math stream. Next likely Tuesday, question mark. Find all integer values such that 2 raised to the 2x squared minus 9x plus 4 is equal to 5, really, x squared raised to the x squared minus x minus 12. Jerks. If we factor. Nah, let's not even bother. 2x squared minus 9x plus 4 times the natural log of 2 is equal to x squared minus x minus 12 times the natural log of 5. Whee! Okay, so we can't divide by 0, so what do we have to do to factor? This is going to get us 8, same sign, gets us negative 9, so that's going to be negative x minus 8x. It's going to be an x, 2x minus 1, and x minus 4. Right? Negative 4, negative 1 makes positive 4. 2x and x makes 2x squared. 2x times negative 4 is going to be negative 8. And negative 1 times x is negative 1. So negative 9 total. Sounds good. Okay, and then here x minus 4, x plus 3. Opposite signs. Natural log 5. And x minus 4 is in both of those, so x minus 4 leaves x equals 4 as a possible answer. Okay. Or 2x minus 1 times the natural log of 2 is equal to x plus 3 times the natural log of 5. Just pretend for the moment that x minus 4 was not 0, so we could divide it out nicely. right? So either x is 4 or x is not 4. If it is 4, then we get zeros in the top, and that's all good, so we're done. If not, then we have to solve this last equation down here. Oy. 2x natural log 2 minus natural log 2 is equal to x natural log 5 plus 3 natural log 5. Subtract them over. 2x natural log 2 minus x natural log 5 is equal to natural log 2 plus 3 natural log 5. Factor out an x, we're left with 2 natural log 2 minus a natural log of 5 is equal to natural log 2 plus 3 natural log 5. X is equal to, nope, I don't want that. I want my calculator. Next question, where'd I put it? There it is. Okay. Parentheses. Natural log 2 plus 3 natural log 5 divided by parentheses 2 natural log 2 minus the natural log 5. Negative 24.7. Yeah, that's going to work. So I guess next question on this, number 16, what was the find all integral values of x such that? So x equals 4. Space 16. So that one, in theory. Repeating decimal point 33333 is base 10 fraction 1/3. Same repeating decimal in base 9 can be written in reduced form as a over b, where a and b are base 10. Find the sum a plus b. So what is 0.33333 base 9? Alright, I think I'm going to leave that there, and we'll continue this on In Theory Tuesday. We'll see how it goes. So, I want to thank everybody for coming in, and we're going to see whom we can raid tonight. Round. Yeah, that's good. That's fine. I'm fine. Just don't update the app yet. Hang on. Alright, let's go raid boss lady. She's currently working on eco. All right. So thank you everybody for coming in. Thank you for subs and hanging out and all sorts of cool stuff. Hope to see you all on next Tuesday is likely when I'm going to be back, but I mean, wait, no. I'm going to be back tomorrow, but for game stuff. So I could be back any other time between now and Tuesday. And Tuesday is going to be our official math date, but then we could decide to do math any other time of the week. So we'll see how things go. Hope you all have a good weekend, good week, whatever. My name is My name is Obi-Wan Pez. This is N Simplex Pachinko. Have a good night, everybody.